And I'm a senior at Doherty Valley High School in San Ramon, California. And today I'm going to be going over the biophysical, molecular, and cellular factors that influence neural circuits formation and synaptic plasticity. So neural circuits are composed of interconnected neurons that transmit and process information using chemical and electrical signals. The overall formation and function of these circuits depend on the selectivity of synapses, which are the junctions between different neurons. The main goal of the synapses is to modify their strength and efficiency. This process is called synaptic plasticity, and it has long been postulated to mediate experience-dependent remodeling of neural circuits that underlies memory formation at various timescales. So synaptic plasticity can be classified into two main types, short-term plasticity and long-term plasticity. Short-term plasticity refers to comparably short-term changes in synaptic strength, which last from like a millisecond to minutes. And long-term plasticity refers to persistent changes in synaptic strength that last from hours to days. So long-term plasticity is divided into two subtypes, long-term potentiation, or LTP, and long-term depression, or LTD. LTP is when there's an increase in synaptic strength that usually occurs when there is like a repeated activation in a specific pattern or frequency. And LTD is a decrease in synaptic strength that occurs when synapses are weakly or irregularly activated. Both these subtypes play an important role in learning and memory, as they enhance and weaken various neural connections. So some of the mechanisms that regulate synaptic plasticity include the release and recycling of synaptic vessels. These vesicles contain different neurotransmitters that interfere with synaptic transmission, which is the trafficking of neurotransmitter receptors. These receptors in turn modulate the responsiveness of postsynaptic neurons to synaptic inputs. This involves cell adhesion molecules, which help facilitate the formation and maintenance of synaptic contacts. These are influenced by various factors, such as the type, frequency, and timing of synaptic stimulation. Synaptic stimulation is the interactions between different types of synapses and neurons within a neural circuit. So the role of glial cells in synaptic plasticity. Selectivity of glial cells, which are non-neuronal cells that support and regulate neuronal processes, is another element that affects synaptic plasticity. By releasing or removing neurotransmitters, neuromodulators, and growth factors, controlling extracellular ion concentrations and pH, supporting metabolism and antioxidant defenses, altering the blood-brain barrier and cerebral blood flow, and taking part in immune and inflammatory responses, glial cells have an impact on synaptic plasticity. Among the various types of glial cells, astrocytes have been specifically linked to synaptic plasticity because they can create synapses with pre- and postsynaptic neurons and can respond to and modify synaptic activity through calcium signaling and gliotransmission. Astrocytes can also influence synaptic plasticity by regulating the expression and trafficking of neurotransmitter receptors, such as the NMDA receptors and AMPA receptors on postsynaptic neurons. Additionally, glial cells like microglia can collaborate with astrocytes to affect synaptic plasticity in a coordinated way. So the biophysical properties of neurons. Action potentials are electrical impulses that neurons can produce and convey. The integration of synaptic inputs, as well as the generation and propagation of action potentials, are governed by the biophysical properties of neurons. These properties can include membrane resistance, axon diameter, and myelination. These membranes' capacity to hold an electric charge is known as the capacitance. The membrane's resistance to the flow of current is known as the resistance. The length of the neuron's long process, called the axon, which conducts action potentials away from the cell body, is measured in terms of its diameter. A fatty sheath that surrounds the axon and insulates it from its environment is known as myelination. These biophysical properties influence the integration of multiple synaptic inputs from various sources, as well as the speed, strength, and length of action potentials. We can use a few basic concepts of electrical circuits and membrane physiology to understand how these biophysical properties affect synaptic integration and action potential generation. A neuron can be described as an electrical circuit that consists of a voltage source, a resistor, and a capacitor. The voltage source is the ion pump that creates a resting membrane potential that's usually negative inside in relation to outside. The resistor is the ion channel that allows ions to cross the membrane, resulting in an electrical conductance that lowers resting membrane potential. The capacitor is the lipid bilayer that creates a capacitance that stores charge and resists changes in resting membrane potential. So the generation and propagation of action potentials. So the activity of ion pumps and channels affects the resting membrane potential, which is not constant. A neuron's membrane potential differs from its resting state when it receives synaptic inputs from other neurons or sensory stimuli from the environment. These changes are also known as graded potentials or postsynaptic potentials, or PSPs, and they can either depolarize or hyperpolarize the membrane potential, making it more positive or more negative. Neurotransmitters commonly generate depolarizing PSPs by opening sodium or calcium channels on postsynaptic membrane, allowing positive ions to enter the cell. Inhibitory neurotransmitters that open potassium or chloride channels on the postsynaptic membrane, enabling positive ions to exit or negative ions to enter the cell, are the typical culprits behind hyperpolarizing PSPs. The PSPs are combined spatially and temporally by the neuron before being integrated. The term spatial summation describes the addition of PSPs that take place at various like cell body locations, but at roughly the same time. The process of adding PSPs that take place at the same place, but at various periods is known as temporal summation. An action potential is triggered by PSPs that are depolarizing and reach a threshold value at the axon hillock, which is where the axon leaves the cell body. A quick and significant shift in the membrane potential, known as an action potential, known as the action potential, travels along the axon towards its terminals. Voltage-gated ion channels, which open and close in response to changes in membrane potential, produce it. Sodium channels and potassium channels are the two primary voltage-gated ion channel types involved in the production of action potentials. When the membrane depolarizes above a particular threshold, the activation gate of sodium channels open, and the inactivation gate closes after a brief delay. So understanding these mechanisms is crucial for unraveling the mysteries of brain development and function, as well as developing novel therapeutic strategies for neurological and psychiatric disorders that involve abnormal neural circuit formation or synaptic plasticity. And we can't wait to see how this field evolves in the future. I'd like to thank the Talaria Summer Institute and my mentor, Ali Solari, for helping me navigate through this field of research. Before this program, I didn't really have any experience in research, and this program really helped me understand how to get started and learn more about my topic. Thank you.